Hello everyone, in this video we'll be learning as well as solving a problem from the concentric helical spring. So this concentric helical springs are used in order to increase greater spring action or to obtain greater spring force within a given space or to ensure the operation of the mechanism in the event of failure of one of the springs. So here we are having these two set of helical springs which are having a common center or common axis, which makes it concentric helical spring, and we need to analyze these springs based on this problems or criteria given. Here the two coils will be wound in an opposite direction to eliminate any tendency to bind, and here we are having the terminologies. The outer one will be named as 1 and inner parameters of the inner coil will be named as 2. So here by D1 means it is the mean coil diameter of the outer one, and small d1 will be the corresponding wire diameter of the outer coil, and the inner coil parameters D2 is the mean coil diameter and small d2 is the wire diameter of the inner one. So here if we are applying a force of F, that means the entire thing is subjected to a force F, then some part of this load will be taken by the outer coil, that will be called as F1, and the other part will be taken by F2. This will be the terminology. So here we can get into this problem. A concentric spring of an aircraft engine valve is to exert a maximum force of 5000 Newton means here the value of F is equal to 5000 Newton, and this will be split and taken by the individual outer and inner coils, and that individual values we have to find F1 and F2. The axial deflection is 40 mm, that means the deflection Y, which is common for both these springs, is 40 mm, and both the springs have same free length, same solid length. These properties are important, or these statements are important. Same free length, same solid length, and are subjected to equal maximum shear stress. That means in both cases the maximum shear stress within the wire is same, which is equal to 850 megapascal. Here spring index is also same, that is C1 equal to C2 is also same, which is 6. C is the ratio of the coil diameter to wire diameter, and here we have to first find the value of the load shared by each spring. That means F1 and F2 we have to evaluate. Then the main dimensions of both the springs, that is the wire diameters D1, D2, coil diameters capital D1, capital D2, then the active coils, that is I1, I2 we have to find. Also here the diametral clearance to be equal, and it is equal to the difference between the wire diameters. It is given like this. So we will be solving according to this. Here an enlarged image you can see. So here we will be first we will be going for equating the maximum shear stress. We are having the shear stress equation as 8 FD by pi d cube into K. So this is equal to 8 F1 into D1 divided by pi D1 cube into K. K1 I can write it as, this is equal to 8 into F2 into D2 into K2 divided by pi into D2 cube. So here it was given like the spring index is same. Since the K, that means the wall shear stress factor, is a function of C, and C1 is equal to C2, therefore I can write the correction factors, wall shear stress factors K1 and K2 will be same. So this terms will be going out. Then we have F1 into D1 divided by small d1 cube will be equal to F2 into capital D2 divided by small d2 cube. So this is will be the simplified form from the above equation. And also we are having C1 equal to C2. That means C is the ratio of capital D by small d. That means we are having D1 divided by small d1 equal to D2 by small d2. Or in another way we can write like D1 is proportional to D1 and D2 is proportional to D2. So I can write here some constant into this can be replaced with the D1. And here also this can be replaced with the D2. That means some constant. And here also into some constant I can write. Then this will be getting simplified to F1 divided by D1 square is equal to F2 divided by D2 square. This is an important relation that we need to find the individual values of the load shared by the outer and inner coils, that is F1 and F2. Now we will go for another relation based on the clearance. So now we will be calling for this clearance, that is the radial clearance, or 2C will be giving you the diameter clearance. So here I will be going for the radial clearance. C value, how I can represent the C value. This is not the spring index. So this is not capital D, C. This is actually the clearance, small c. So this is the clearance. And here if you are observing, this C will be equal to the center to this distance minus this distance. So if you are observing, this will be equal to the inner diameter of the outer coil, that I can call it as, this will be the D1I, inner diameter of the outer coil, and this diameter will be the outer diameter of the inner coil, that is D2O. So I can write the clearance, that is small c, equal to D1I minus D2O. And we are having D1I is equal to capital D1 minus small d1, capital D1 by 2 minus small d1 by 2, minus of D2O we are having, this is actually D1I by 2 and this is D2 by 2. So these are half diameters divided by 2. And the D2O by 2 can be written as D2 divided by 2 plus capital D2 divided by 2. So this one I can write it as D1 minus D2 divided by 2 minus of D1 by 2 plus D2 by 2. Like this I can write. So this is the clearance, small c. And it is given that the diametral clearance is equal to the difference between the wire diameters. Here we have evaluated the radial clearance. If diametral clearance is equal to difference between wire diameters, then this will be equal to half of the difference in wire diameter, because this C is the radial clearance. So this is the radial clearance. So I can write the expression. This is obtained from this statement. This statement I have represented here, and the right hand side I can write this like this, which is D1 minus D2 divided by 2 minus D1 divided by 2 plus D2 divided by 2. So if you are simplifying, you will be getting an expression for D1 minus D2 by 2, because here minus D1 by 2, this minus D1 by 2 will be coming onto this side, then it will be getting added with this D1 by 2, and this minus D2 by 2 will be coming and added with the minus D2 by 2, that is that term will be getting cancelled. So here we will be getting final simplified expression as capital D1 can be written as capital C, that is spring index into small d1 minus spring index into small d2 divided by 2 equal to d1, and this can be simplified to, finally we will be getting the d1 by d2 as c divided by c minus 2. This expression we will be getting at the end of this one. So here we are having the expression ratios of wire diameter d1 by d2 as c divided by c minus 2, and from earlier derivation we have obtained this f1 by d1 square equal to f2 by d2 square, or we have obtained the f1 by f2 as d1 divided by d2 the whole square. So these expressions are important for solving our problem. So once again we will be going to the problem. So here the spring index value is 6. So with this I can find the value of this ratio, that is d1 by d2. So the d1 by d2 for our problem, d1 by d2 will be becoming, c value is 6, so divided by 6 divided by 6 minus 2, which is 4. So 6 by 4 we will be getting as 1.5. So from this I can find the value of f1 divided by f2. This will be equal to d1 by d2 the whole square, which is 1.5 square, and this value will be equal to 2.25. So from this I can write f1 equal to 2.25 times f2. So this is one equation, and in the beginning we are knowing that this force 5000 will be shared by the outer and inner coil. So I can write f as sum of f1 and f2. So I can write another equation. The f1 plus f2 can be written as f, which is given as 5000 Newton. So this is the second equation. So sum of f1 and f2 is 5000, and f1 can be written in terms of f2 as 2.25. So these two equations can be solved simultaneously for finding the values of F1 and F2. Here we will be getting the expressions or values of F1 as 3462 Newton and the F2 as 1538 Newton. So this is the answer for the first part. In the first part, it was asked the total load shared by each spring. So we have evaluated the values of F1 and F2. Now we need to find the values of the dimensions of each spring. So dimensions means the wire diameter small d1, capital coil diameter capital D1, and similarly small d2 and capital D2 we need to find. For that we were given with the allowable shear stress. The tau max was given. Tau max is equal to 850 megapascal, and we are having expression for this one, which is 8 F1 D1 divided by pi D1 cube into K1 we are having. The same can be equated to the second coil also, that is inner coil also, 8 F2 into D2 divided by pi into D2 cube into K2. So here we are having or I can rewrite this as 8 into F into 1 D1 by small d1 I can take like C1 divided by pi into D1 square into K1. I will be taking this expression first, 850, for solving or for finding the value of diameter. So here left hand side is 850 and the value of F, force acting F1, that is just before we obtained, which is 3462 newtons. C1 value we are having, C1 value is 6, and K, all shear stress factor we can evaluate. We are having the expression from the data book, 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. So here C value is 6, you can substitute, then the value of K will be getting equal to 1.2525, and only unknown in this equation will be then D1 square. So from this we can find the value of D1. If you are solving this D1, we will be getting an around 8.83 mm. So we will be standardizing it to the next higher value, which is 10 mm. So from here we obtain the value of D1. Then capital D1 we can evaluate, which is simply the C, spring index into small d1, and spring index is 6, so it will be equal to 60 mm. In a similar way, I can equate this term to the tau max, that is 850, like this, like similar to this way. Then we will be getting the value of small d2 at the end of simplification and solution. Here the value of D2 will be getting around 5.88, then we will be standardizing it to 6 mm. Then the coil diameter, the inner coil diameter will be equal to C, which is 6 into 6, C into D2. Finally this will be equal to 36 mm. So these are the dimensions of the spring also we have evaluated. This was also one part of the question to solve. Next is to find the number of active coils in each spring. For that we will be making use of the equation for deflection. So here deflection Y equation we are having, Y is equal to 8 into F1 into C1 cube into I1. I1 is the number of active coils in the outer coil, divided by G into D1. Here the rigidity modulus is also same for both the springs. So here we can substitute the values of Y. Y is actually 40 mm given. So this is 40 equal to 8 into F1, which is 3462 into C1 cube, which is 6 cube. I1 is the unknown. Divided by G is 80 GPa or 80 into 10 raised to 3 megapascal or Newton per mm square. Here all things are substituted in Newtons mm and Newton per mm square, and D1 value is 10. So from this we will be getting the value of the active number of coils, which is I1, and here we will be getting a value of around 5.35, but we need the a full digit number of turns of coil, so we will be taking to the next full digit number, which is 6. So here also, similar to the simple problem of helical springs, we can assume a suitable end condition. So end condition can be assumed, and here we will be assuming the squared and ground condition. So square and ground condition can be obtained. then we are having the total number of coils for the inner or the first outer coil. That means I1 is 6, then IT1 will be equal to 6 plus 2, 8 value will be getting. So this is the total number of coils. In the question it was mentioned that the solid length of both outer and inner coil are same. So if total number of coils is IT1, then we can have the solid length. So the solid length of the first coil or the outer coil LS1 will be equal to the number of total coils into the wire diameter. This is also from the basics. So this will be equal to 8 into wire diameter is 10 mm. So this will be equal to 80 mm. Since it is mentioned that both the outer and inner coil are having same solid length, I can write the solid length of LS2 also as 80 mm. This will be can be equated to similar to this expression. I can substitute here the total number of coils in the second or the inner coil within the concentric into its wire diameter. So D2 value we are having, which is 6 mm. Then we can solve for the total number of coils for the inner one, that is IT2. This will be equal to 80 by 6, around 13.3 will be getting. So we will be rounding into 14 number of coils. This is total. We need to find the actual number of coils or the active number of coils, which is I2, and this will be 2 lesser than. If here also we are assuming the same end condition, that is coiled and ground, then this will be equal to total number of coils minus 2. Then we will be having the 12 number of active coil. So here also we have evaluated the active number of coils in the outer coil within the concentric, which is 6, and the total number of coils within the inner, that is 2, which is 12. So this is the solution for the third part. Now we have solved all parts of this question. First we evaluated the share of load that is carried by the outer and inner coil. Then we have calculated the dimensions, the wire diameter as well as coil diameters. Then we have evaluated the total number of active coils within the outer and inner. So this is the way to solve a problem from the concentric helical springs. This is basic. If you are knowing the procedure for simple helical spring, the same can be extended or applied to this one also. So that's all for this lecture. Thanks for watching.